Welcome all in the course of SAR data processing and its application with special emphasis on Reset 1A ES4. Myself Ashish Joshi, working as a scientist at Photogrammetric and Remote Sensing Department at IIRS Dehradun. So in this course the major topics are the SAR remote sensing concepts, in which we will learn about the SAR geometry, imaging modes, Reset 1A ES4 modes, SAR resolutions, geometrical distortions, SAR image properties and interpretation. Then we have two sessions on the SAR data processing. In session 1, we will learn about the SAR data, raw data processing, in which we will learn about the pulse compression technique, synthetic aperture concept, RCM, which is called as range cell migration, range Doppler algorithm, and Reset 1A ES4 SAR parameters. So in each lectures we will first learn about the SAR concepts and then how to it is applied on the Reset 1A ES4, which is the Indian SAR satellite launched on 2022 in the month of the February. In the second session of the SAR data processing, we will learn about the SAR geometrical and radiometric corrections techniques, geolocation, geocoding, speckle filters, and Reset 1A ES4 SAR products. Then we have two applications like SAR polarimetry and SAR interferometry. In the SAR polarimetry, we will learn about the basic concepts of SAR polarimetry, what are different decompositions, what is hybrid polarimetry and quad pole polarimetry, and what are the modes in the Reset 1 for the polarimetry. And in the SAR interferometry lecture, we will learn about the interferogram generation and processing, baseline concepts, across track and along track interferometry, and we will also see some of the results in the Reset 1A ES4 SAR interferometry. So let us start with our first topic, which is the SAR remote sensing concepts. So now what is the outline of this lecture? So we have the basic concepts of the SAR remote sensing, which is the SAR imaging concepts, resolution, geometry, imaging modes, and the SAR image properties and interpretation, in which we will learn about the target parameters, sensor parameters, and at last we will see the ES4 satellite modes and its specification. So basically the remote sensing is divided in the three regions of the electromagnetic spectrum. We have the optical remote sensing, in which we will learn about the reflected sunlight in the optical range of 0.4 to 0.7 micrometer and the near infrared. And second is called the thermal infrared remote sensing, in which we will learn about the emitted radiations. Okay, so first in the optical we will basically deals with the reflected sunlight, and in the thermal we will basically concentrated on the emitted radiations in the thermal infrared region, which is working on 3 to 14 micrometer. So next is the microwave remote sensing. So microwave remote sensing, in which we will learn about the backscatter radiation in the microwave region, which is in the larger wavelength of 0.01 to 1 meter. So normally in our optical wavelength we will use lenses and mirrors for focusing, but in the microwave region we will use the antenna for focusing. So in this figure we will see this is the optical wavelength and this is the non-optical wavelength. So in the non-optical wavelengths we will have the microwave remote sensing. So in microwave remote sensing we have different bands, which is Ka band, Q band, X, C, S, L and P, where in the space band we will mainly see the X band, C band and S and L band, and P is mainly in the airborne data we will have in the SAR. So in the microwave remote sensing we have two types of sensor. One is the active sensor and second we have the passive sensor. In the active sensor we have the SAR, which is in the imaging, and second is the spectrometer, which is the non-imaging, and it used the backscatter information for the ocean surface, and it is used for studying the wind speed and direction near the ocean surface. Next is the altimeter, which is the non-imaging, and it measures the surface topography and the height of the topography. And next is the passive sensor, which is mainly a radiometer. So in the radiometer, it sends the microwave emissions from the earth surface. So now what is the SAR remote sensing? So the SAR is the imaging radar. It is an all-weather observation system, and it is an active sensor sensitive to dielectric properties of the medium, which is the water content and humidity, and sensitive to the surface roughness. SAR responses increases when the moisture or roughness increases in the soil. It has the penetration capabilities, sensitive to topography, and it has also have the polarimetric capabilities. It is very much sensitive to the metallic and artificial objects, and sensitive to the geometrical structure. So these are some of the benefits of the SAR remote sensing, which work on all weather 24/7 in the day, night, and basically it is very much sensitive to the artificial objects like man-made objects. It is very much have the higher backscatter. The limitations are actually it has the complex interactions, means we should have the proper understanding of the different scattering mechanisms in the physics. And it has the speckle is a type of noise in the image, so that is actually affecting the SAR image. Okay, and it also have some distortions when the topography is there. So there, if we acquire the data, so it initially it has the geometrical distortions, but with the some processing we can remove that topographic effects by the process of the terrain corrections and the geolocation. Now what is the potential of the SAR? So with respect to the optical imagery, we have the double capacity, because in SAR we can have the imaging in the day and as well as in the night. So as compared to the optical, we have the twice data, and it is insensitive to the cloud cover, means because it works in the microwave region, so it has the very much larger wavelength, so it can penetrate the cloud. So we have the 5 times data more as compared to the optical data. So if we will combine this day night operations concept of the SAR, and it is insensitive to the cloud cover, so we can have the 10 times more images are available in the SAR. And as compared to the optical, it has multiple incidents, means we can operate the SAR in different look directions, and it has the multi-resolution, means normally the optical sensors have the fixed one resolution, but in case of SAR we can have different modes. So at different modes we can have multiple resolution at each modes. So as per our application we can choose our modes, means if we want to have the higher resolution data, then we can have the spotlight mode, and if we have the normal resolution we can have the strip map mode, or for the large swath we can have the coarse resolution. So what is the difference between the RAR and SAR? So what is the RAR? It is a real aperture radar. So normal real aperture radar is a normal physical radar. It also uses the microwave region, and energy emitted the across track region it will sense, and it is sense the return time, means how much time delay it is there, so it will give the slant range, and what is the amount of energy it is scattered. So normal actually radar we will have only the time delay concept. Okay, so means how much time we are getting the signal, so that time and some backscatter information we will have. So we cannot have the images from the normal radar. Okay, so that is called the real aperture radar. But if we will use the synthetic aperture radar, which is called the SAR, that is a imaging radar. Okay, so normally the real aperture radar is a non-imaging, but if we will have the concept of the synthetic aperture, then we can have the images out of the SAR, because in the remote sensing basically we will use the images for our interpretation and different applications. So for the images we have to use the synthetic aperture radar. So we have the higher resolution in both the range and azimuth. So what is the range and what is the azimuth? So if you can see, this is the radar and it is moving in this direction, it is the flight direction. So this direction is called the range, which is called the across track direction, and this is called the azimuth, which is called the along track direction. Okay, so how the higher resolution we are getting in the synthetic aperture and not in the normal radar? Because we have one synthetic aperture concept. We have this extended antenna simulated by the forward motion of the platform. So as this radar is moving, so this radar will form a synthetic, a very much larger aperture of this antenna, and this larger aperture is actually responsible for getting the very much high resolution in the azimuth direction. Okay, so what is the synthetic aperture concept? We will learn in the second session, which is called the SAR data processing 1. So there we will learn about the synthetic aperture concept. Okay, so in this synthetic aperture, what it is there, we are getting a very much higher resolution in the azimuth direction. So we have different SAR satellites like Reset 1, IIRS and RadarSat, which are the SAR satellites, and it is generating the high resolution images. So what are different SAR transmission features are there? So basically in the SAR transmission we can have the 4 main parameters. One is the frequency, means at what frequency we are sending the electromagnetic radiation. Second is the propagation direction, means at which direction we are sending the electromagnetic radiation. Third is at which power, what is the power, because we have to send some electromagnetic radiation, so what is the transmitted power. And fourth is the polarization, at which polarization we can send, means we can send at a horizontal polarization or as a vertical polarization. So as I told you, the SAR is an active sensor. Active sensor means it can have its own illumination. So SAR or radar will send the electromagnetic radiations in the microwave region, but in the optical remote sensing we have the passive sensor, means it is depending on the sun energy, so it is a passive sensor. But SAR is an active sensor, so it can transmit the electromagnetic radiations in the microwave region. And how to generate that signal? It is the dependent on 4 main features, like at which frequency we can send, and which is the direction, like look angle, what is the transmitted power, and polarization. Okay, so a frequency we can say we have to send the signal at the C band, S band, L or P band. Okay, so these are the 4 major parameters we have to consider before designing the our SAR sensor. So what is the synthetic aperture radar? So as I told you, it is an active sensor, so it will transmit one electromagnetic radiation which is called the pulse. Okay, so this pulse is transmitted from the antenna. So you can see in this is the SAR and it is transmitting a pulse. So this is a pulse, and this pulse will interact with the earth surface with the different features. So after interacting, it is actually there will be a phenomena which is called the scattering. So scattering will happen and some of the energy will come towards the SAR sensor. Okay, so that is called the backscatter energy. Backscatter means some of the energy which is going towards the sensor, that is called the backscatter energy, and this backscatter energy is sensed by the SAR sensor. Okay, so this energy is amplified as a voltage and it is recorded as a digital number. So when it is observing the SAR, when the SAR is taking the earth's surface, then we have the raw data generation. So initially the data is in the form of the raw SAR data. So you can see this is the data what we receive at the ground station from the satellite. So this data has actually some information, but we are not able to see the features in this image. So it is in the uncompressed form. Okay, so we will do some signal processing technique which is called the SAR data processing. So at the ground station we will do some processing which is called the signal processing techniques, and we will generate the focus SAR data. So that is called the focus SAR data. So mainly users will find out this type of data. So users will get this type of data, and from there L0 to raw data at the ground station, and the data processing team is there, and we will process the data and we will generate the different level products, like this is a level 0 product, level 1 product, and after that also we will do some post processing and generate the level 2 products. Okay, so this is the entire process or brief overview how the SAR image is acquired the data. So SAR is a side looking radar system. Okay, so it is not a nadir looking, because unlike the optical sensor it is a nadir looking, but the SAR is a side looking system, and it will actually take the images either in the left direction or in the right direction. So say this is the SAR and it is illuminating in the right direction. So this is called the footprint. Okay, so this is called the footprint, and this angle is called the theta angle, and this is the height of the sensor, and this range is called the slant range. So SAR is a side looking radar system which makes a high resolution images of the earth surface. Continuous strips of the ground surface are illuminated to one side of the flight direction. Signal is recorded, and digital signal processing techniques in the ground are used to focus the image and obtain the high resolution images. So as it is moving, so we can have it is actually past one pulse. That pulse is interact with the ground surface, and it is backscattered towards the sensor. So this is the energy it will write. So it will write first pulse, second pulse, third pulse, fourth pulse, and you can have this 2-dimension data, or it is an image. This direction is called the range direction, this is called the azimuth direction, and this is the flight direction. So this across track distance is called the range, and this along track distance is called the azimuth. So this actually synthetic aperture radar, we have the concept of the time delay. Okay, so the synthetic aperture radar or SAR observe the strength, means it observe the backscatter energy, and also one term is called the time delay. So time delay is called the ranging of the return signals. So as you know, the formula of time is equals to distance upon speed. So here you can see if this pulse is sent towards the ground, so initially it has the r distance, but the pulse is actually first it is transmitted, it is convolved, or it interacts with the earth surface, and it is backscattered towards the sensor. So this pulse is actually traveled 2r distance. So time is given by the 2r by c. So you can see from this formula, so how we are getting this range is given by c tau by 2. Okay, so this range is calculated through the time delay. Okay, so in the SAR we have the most important term for the geolocation or having the precise location, because it accurately calculate this time delay. So if we will measure this time delay accurately, then we can measure this range. Okay, so this actually in SAR we are getting automatically the range to the target. Okay, and second the backscatter energy. In optical sensor we are not getting the range directly from the sensor. We have to do some of the geolocation algorithm from the roll pitch yaw to get the range out of it, but here we are directly getting the range. So in the optical sense we are getting the range indirectly, but in the SAR we can get the range directly from the sensor with the help of the time delay concept. So as I am saying, like SAR is transmitting electromagnetic radiation in the microwave region. So that transmitted electromagnetic radiation is called the chirp or pulse. So this is, you can have the some basics of the electromagnetic radiation, like it has the wavelength. So what is the wavelength? So this is the electromagnetic radiation. So distance between the successive crest of the electromagnetic wave, so that is the wavelength. And frequency is the number of the crust that pass through a fixed point in a given amount of time. So from the formula, C is equals to lambda nu. Lambda is the wavelength and nu is the frequency. So we can have the frequency as C by lambda. And third term is of the pulse is the pulse width, means what is the time duration of this pulse. So that is called the pulse width. Okay, so that is the time duration. Next is the PRF. What is the PRF? PRF is the pulse repeating frequency, like the number of pulses transmitted per second. Okay, so means if we are sending the signals, so at which frequency we are sending the signals. So the rate of sending that electromagnetic radiation or chirp is called the pulse repeating frequency. Next is the pulse repeating interval, means what is the time gap between the two pulses, that is called the pulse repetition interval, or it is the 1 by PRF. Okay, so if we are having what is the time between two pulses, that is called the pulse repeating interval. And last is the sampling frequency. What is the sampling frequency? The frequency at which pulse is sampled for a conversion of pulse from analog to digital. Okay, because we have the pulses, so that pulses are basically in the analog in nature. So at which frequency we have to sample that pulses to convert from analog to digital, so that is called the sampling frequency. So how many samples we are getting? We are getting the number of samples as sampling frequency into the time duration. So that that samples we are getting. So as I told you, like SAR is a like imaging sensor. So if we know the what is the sampling frequency of the chirp and what is the time duration, then we can calculate the number of samples. So in this slide we have this and this is the range and this is the azimuth. So how many samples in the range? So that is calculated through this formula, Fs into tau. Then we can calculate how many number of samples is there in the image if we know the SAR parameters like sampling frequency and the pulse duration. So normally the optical has the 1 resolution, but in case of SAR it has the 2 resolution. One is called the range resolution and second is called the azimuth resolution. So the range resolution corresponding to the minimum distance between the 2 points in the range direction, which can be separated by the SAR sensor. Okay, so that is normal resolution. So as I told you in my previous slide, we have this SAR image and we have this range direction and this is the azimuth direction. So what is the resolution we are getting in the range direction and what is the resolution we are getting in the azimuth direction? That is called the range resolution and it is called the azimuth resolution. So the basically the range resolution is mainly depends on the pulse bandwidth. Okay, so that is if we have the pulse bandwidth of say 75 megahertz, 150 megahertz and 750 megahertz. So actually if we are using the C band, S band or it is X band, so there is some bandwidth we have for that SAR sensor which is allocated for the particular sensor. So for the X band we can go up to the 750 megahertz. So like for the if we are considering the 250 megahertz, then we will just C is the speed of light and 2 and B is the bandwidth. Then we can have the resolution range resolution of 0.6 meter. So we can see this is the range resolution and that is the bandwidth. So this range resolution is inversely proportional to the bandwidth. If we have the signal of higher bandwidth, then in the range direction we can have very much higher resolution. So if we want to have the higher resolution, so we can have the higher bandwidth of the signal to get a better range resolution. And second is the azimuth resolution. Azimuth resolution is actually we are getting through the synthetic aperture approach. So that both concept will be detailed in the next lecture, which is called the data SAR data processing. So why that is C by 2B and why this is L by 2, we will learn in the next SAR data processing lecture. So normally the SAR range resolution is actually the C by 2B, and azimuth resolution normally is L by 2, means what is the length of the antenna. The azimuth resolution is given by L by 2, means if the length of the antenna is 12 meter, so azimuth resolution we will get around 6 meter by using this synthetic aperture concept. Okay, so basically we have seen like SAR has the two resolution, one is the range direction and one is the azimuth direction. In the range direction, the actually the resolution depends on the bandwidth, and in the azimuth direction the resolution is depending on the length of the antenna. Okay, so if the length of the antenna is L, then we are getting the resolution of L by 2. So this is the typical geometry of the SAR. So we can have, this is the, say this is the azimuth direction, means SAR is moving in this direction. So it is looking in particular direction. Okay, so this is called the look angle, and the point which is directly opposite to the perpendicular to the SAR sensor, that is called the nadir point. And this is called the how much is the beam, so that is called the beam width. Okay, and this is the first point where the beam is called the near range, and the last point is called the far range. And this is the incident angle. So this is the look angle which is the SAR beam is forming with respect to the nadir, so that is called the look angle. And incident angle, which is the SAR beam is actually measuring with the normal to the surface, so that is called the incident angle. So for the plane surface, this look angle is approximate equals to the incident angle. And how much is the actually this is the length, that is called the swath in the x direction. Okay, so these are some of the terms. One is the look angle, what is the incident angle, near range, far range, nadir. So this is the geometry of the SAR, and SAR is always a side looking sensor. So why the SAR is side looking? So say because SAR is a ranging device, so if we are considering it is a nadir looking, okay, so you can see these two targets T1 and T2 will have the same range if it is a nadir looking. And as I say, like SAR is a ranging device, so it can differentiate two targets separately if it is having the different ranges. But if it is a nadir looking, you can see this T1 and T2 target have the same range. So the SAR will not able to distinguish these two target separately because it has the same ranges. Okay, so we will have this left right ambiguity. So how it is solved? So now if the SAR is a side looking, so you can see these two targets will have the different ranges. So it have the R1 range and it is having the R2 range. So by using this side looking concept, we can say it will remove this right left ambiguity because each target have the unique range, and with the help of the SAR time delay concept, we can distinguish each target because each target have the different ranges. But in the nadir looking, these two targets have the same range, so we are not able to distinguish two targets separately if the SAR is the nadir looking. So that is the major principle why the SAR is side looking. So always when we are talking about the synthetic aperture radar in which we are getting the high resolution images, the SAR is always the side looking geometry. So what are the different imaging modes in SAR? Okay, so basically the classically we have the three major modes of the SAR. One is called the strip map, second is called the spotlight, and third is called the scan SAR. So what is the strip map mode? It is actually in the strip map mode we have the continuous image is formed with the motion of the SAR. So you can see here, you can this SAR is moving and this is having a continuous strip. Okay, so it is a synchronous imaging, and long imaging strips will have. So we can have the limited azimuth resolution L by 2 and limits swath in the range. Okay, In the spotlight mode, actually what the sensor will do this in this actually, it will continuously looking a particular area of a earth surface. So we have this spotlight mode. So what is the benefit of the spotlight mode? We are having a very much high resolution in the spotlight. Normally the azimuth resolution is get the L by 2 in the strip map mode, but if we want to have a higher resolution than L by 2, so like if the length of the antenna is of 12 meter, and then in the strip map mode we will get a resolution of 6 meter. But if we want to have a better resolution, then we can go to the spotlight mode. In this spotlight mode we will get the better resolution than L by 2. Okay, so better than 6 meter also we are able to get from the antenna of 12 meter. So the benefit is the very fine azimuth resolution. So these three modes actually have the different resolutions, and in the both in the range and azimuth, and they have some of the merits and demerits. So the merit of the spotlight, we are getting the very much higher resolution, but the limitation is because it is seeing this surface, limited surface, so we have very much limited azimuth swath. The range swath is same like strip map, but in the azimuth direction the swath is it is very much reduced. Okay, so we have this L by 2 resolution here in the strip map mode, but better than L by 2 using the using the spotlight mode. Third is the, because in the strip map and this one we have the limited range swath. So how to increase the range swath? So we will have the SAR mode. In the SAR mode, the swath is increased by use of the antenna beam, which is electronically steerable in the range direction. Okay, so we will use different beam concept. So we have one beam, or we can have the three beams. So first beam will look in this direction, second beam and third beam in this direction. So in this way we can have a longer swath in the range direction. Okay, so SAR actually is used for having the larger swath in the range direction. Okay, so we have basically these three modes. One is the strip map mode, one is the spotlight mode, and third is the SAR mode. The strip map mode is used for the normal synchronous imaging, which have the limited azimuth resolution L by 2 and limited swath. In the spotlight mode we have the higher resolution in the azimuth resolution, and we have the limited azimuth swath and range swath. But in the SAR mode we have the very much larger swath, but in the cost of the resolution. Here in the SAR we will use the multiple beam concept. Okay, so this multiple beam will form the swath in the range direction. So these are some of the basic concepts of the SAR imaging geometry, imaging modes, and why the different resolutions of the SAR. Next we will see the SAR image properties and its interpretation. So what is an SAR image? Okay, so SAR image is seen as a picture. Okay, like the optical, we have the two-dimension image here. Pixels are the digital numbers. Okay, so that is the DN values we are getting. The image is affected by the speckle noise, so it is not as clear as the optical images. So here you can see some kind of noise which is called the speckle noise. Image is interpretable based on understanding of the physical process. So because in the SAR actually it is the basically the scattering processes involves for the different different targets or different features of the earth surface. So we have different scattering for different targets or the features. Okay, so we have different responses or backscatter energy for different features. So we have to know about this scattering principles for the different features of the target. So that SAR image interpretation is not a straightforward. We have to have some physics, knowledge of physics behind it, and requires some familiarity of the ground surface being imaged. Okay, so we should have some prior knowledge of what is the target we are seeing. Okay, so here we can, in this image we can see some of the brighter targets are there, and darker targets are there. So it actually it formed with the scattering principle, backscatter energy. So this digital numbers in the SAR is actually the backscatter energy which is getting. So unlike in the optical sensor, we are getting the reflected energy. In the thermal sensors, thermal images, we are getting the emitted energy. Emitted energy means when the earth surface is heated and some energy is, after some time, some energy is emitted, so the sensor will sense that emitted energy, so that is called the thermal imaging. Okay, but in the microwave region in the SAR, we are having the backscatter energy, means SAR is sending some signal, it is interacting with the earth surface and the scattering will happen, and this backscatter energy is coming towards the SAR. So this SAR backscatter is contains the information about the earth surface which derive the reflection of the radar signal, means after this when the SAR signal interact with the earth surface and some of the energy comes back towards the SAR, that energy is called the SAR backscatter. So the backscatter of SAR mainly depends on two parameters. One is the target parameter and second is the sensor parameter. So what are the target parameters? Means when the SAR image we are forming, then the SAR signal is interact with the earth surface. So this backscatter energy actually depends on the what type of feature it is interacting, means it is interacting with this what is the roughness of the feature, what is the dielectric constant, and what is the how is the terrain slope or local incident angle of this of the feature. And second, what is the sensor parameter, means we are sending some electromagnetic radiation, so at which wavelength we are sending, because I have already told you the SAR can have either image in the C band, X band, L band. Okay, so at which frequency or wavelength we are sending the signal. And second is the look angle. So look angle is the at which direction or at what angle we are sending the SAR signal. So it also depends if the look angle is low or high, so it also affects the backscatter. So the backscatter of the SAR will depend on the two parameter, target and the sensor parameter. So target are the surface roughness, dielectric constant and local incident angle, and the SAR parameters are the wavelength, look angle and the polarization. So because that electromagnetic radiation we can design in such a way that we can transmit this pulse or the chirp in a particular polarization, like in the horizontal or vertical polarization. So at which polarization we are sending the SAR signal. So first we will learn about the target parameter. So first is the surface roughness. So for the surface roughness we will follow the Rayleigh criteria in case of SAR. So what is the Rayleigh criteria? So Rayleigh criteria for the smooth surface, if we have any surface, okay, so this is the undulations. So this undulations in the surface is called the height or surface undulations H. So this H, if it is less than this parameter lambda by 8 cos theta. So what is the lambda? So lambda is the wavelength, means this backscatter energy will depend on the wavelength, and this theta is also the incident angle or look angle. Okay, so the SAR will say for a particular surface is a smooth surface if it is following this criteria, means the undulation in the surface it is less than lambda by 8 cos theta, then for the SAR the target is a very much smooth target. Now for the smooth surface, if we are sending some SAR signal, so for the smooth surface it will follow the Snell's law. So no energy is coming back towards the SAR. Okay, so means if we are sending some signal, all the signals will reflect it away from the SAR. So this is a SAR sensor and we are sending some signal, and all the energy are going away from this sensor. So we are getting no energy if the surface is smooth. So for a case of the smooth surface, we are getting a very much darker return, because if we are getting a high backscatter energy, then we are the brighter returns. Okay, because the energy is high, then we have the brighter returns, and in image it will appear as a white in tone. And if the surface is smooth, so there will be having a specular reflection. Specular means all the energy will go away from the sensor, and we are getting a very much less energy, so that region will appear darker in the image. Okay, so if the surface is rough, then we can get some of the energy towards the sensor. Okay, so if the surface is smooth, no energy will come back to the sensor, and it will appear as a darker tone. And if the surface is rougher, and how this surface is smooth or rougher, if it is following this Rayleigh criteria. Okay, so if this is following this one, if the surface is rough for the SAR, then we have the medium backscatter. Okay, and if we are in very much higher rough surface, then we have the higher backscatter. Okay, so the main thing is that if the surface is rougher, then the backscatter will be higher. If the surface is smoother, then the backscatter is lower. So in case of SAR, if it is the darker region, so it is actually we are considering a low backscatter. So if there will be any smooth surface like ground or water body, so it will have a very much darker returns, because it is appearing as a smoother surface, and specular reflection will happen. But if any surface is very much rougher, then we are getting the higher backscatter. Second is the dielectric constant. So we are telling one by one of the target parameters. So first is the surface roughness. So for the surface roughness, if the roughness is higher, then we are getting the higher backscatter. And second is the dielectric constant. So the dielectric constant is a measure of the reflectivity and conductivity of a material. The dielectric constant influences the ability of material to absorb, reflect, and transmit the microwave energy. Higher the dielectric constant, higher will be the backscatter. Okay, so like if the dielectric constant of any material is higher, then we have the higher backscatter. So like water and metals will have the higher dielectric constant. Dry natural materials have the low dielectric constant. The presence of moisture increases a material's complex dielectric constant. So in the microwave region, most dry natural materials will have the dielectric constant from 1 to 8, but water on the other hand has a dielectric constant of approximately 80. Okay, so when any soil is actually mixed with water, then or soil if the soil has the soil moisture, so we have the brighter return, because normally the soil have the lower dielectric constant, then we have slightly lower backscatter. But as the water is mixed with the soil, so it will have the higher dielectric constant. So the soil moisture will have the brighter returns. And normally like a pond or a river, it has the water, but due to the specular reflection, it will appear as a darker. Okay, so water body will appear as a darker due to the smoothness. Okay, because there will be a specular reflection is happening. But in case of when the water is mixed with the soil, then it will have a brighter returns, because there the dielectric constant will dominate. Okay, and in case of the pond or river, it will the specular reflection will dominate. Third is the local incident angle. Local incident angle, in case of this, you can see if this is the range of the SAR. So if this slant range is making the angle with the normal to the terrain, so and that is called the local incident angle. So here you can see this is the normal of the terrain. So what this slant range is making with the normal to the surface, that is called the local incident angle. Okay, So as we have the different terrain, so this local incident angle will decrease. Okay, so this, when you can see their slope is increasing, this local incident angle is decreasing. So a small local incident angle results in the brighter radar returns. Okay, so when there is a terrain, okay, so there is a terrain, and we, as the terrain is increases, and the slope will increase, and there the local incident angle will decrease. Okay, so this local incident angle when decreases, so we have the higher backscatter. Okay, so this mountainous areas will appear as a very much brighter returns. Okay, so this local incident angle due to the terrain slope will also increase the backscatter energy. So we have seen these three parameter of the target. So we cannot see, we cannot interpret any feature on the SAR only based on one parameter. We have to see different target parameter, like what is the roughness of the feature, what is the dielectric constant, and what is the local incident angle. So it will actually depends on the darker and brighter regions in the SAR based on the backscatter energy. So we have three parameters. So if we have to see, this image tone refers to each distinguishable gray level from black to white proportional to the strength of the SAR backscatter. So in the SAR image we have the, if we have a black and white image, so we have the gray scale from darker to the brighter. So this darker to the brighter is proportional to the strength of the SAR backscatter. If the SAR backscatter will be higher, then in the SAR image it will appear as a brighter tone, and if it is a lower, then it will appear as a darker tone. So relatively smooth targets like calm water appear as a dark tones. Diffuse targets, diffuse means which is having the some roughness and some vegetation, it will have the intermediate tones. And man-made targets, artificial targets like buildings, ships, may produce the bright tones depending on their shape, orientation, and the material. Okay, so you can see the darker regions will have this calm water body will appear as a darker, vegetation appear as a medium tone, and the man-made materials will appear as a brighter in the SAR image. So you can see in this one, you can see this is the air strip. So you can see this is very much smoother. So this is smoother, you can see it is appearing as a very much dark tone, and in here you can see there is a buildings, urban things, all man-made targets are there, so it is appearing as a brighter returns. Okay, and this is the water body. So this, due to this specular reflection, it is appearing darker. So all the smooth things, due to the specular reflection, it will appear darker in the SAR image, and this brighter thing will appear due to the man-made targets. Okay, so you can see calm sea surface appear darker in SAR image, while rough sea surfaces may appear bright, especially when incidence angle is small. So normally the sea surface is happening is appear dark in SAR images, but once any wind is happening, okay, so there will be some waves in the oceans, so it will appear as a rough sea surface. Okay, so for this rough sea surface, again the concept of the roughness, as the roughness is increases, so the we have the more backscatter. So calm sea surface will appear as a darker tone, but if it is a windy type of thing, then we can have the rough sea surfaces, and they have some higher backscatter as compared to the calm sea surfaces. And you can see the oil spill. So oil spill is again a very much smooth feature. So in you can have in the ocean, you can detect the oil spill because it is very much smooth in the ocean surface. So this is the oil spill in this one. Trees and other vegetation like natural vegetation are basically have the medium backscatter. Okay, so man-made targets will have a very much higher backscatter, smoother surface will have a very much lower backscatter, and the vegetation will have a intermediate backscatter. So here you can see the man-made different target or features, you can see this is the ship and in the oceans. So ship detection in the SAR images is very much good as compared to the optical, because in the SAR images we don't have clouds first. Secondly, SAR image, we have the ocean which is having the very much specular background, so it is appearing very much darker in SAR image. Secondly, this all ships are the main met targets, so it is appearing very much brighter in the SAR image. So the ship detection and in the automatic way, it is very much good in the SAR images as compared to the optical images, because we have the very much higher return in background of the very much low backscatter like a sea surface. Here you can see the built up areas and you can see due to the main met targets, it will appear as a brighter tones. Here you can see the oil containers, it is appearing as a brighter tones. So this is the SAR image typically. So you can see this is the oceans, okay, and you can see these are ships which is appearing as a bright tones, and this water body is appearing as a specular scattering due to the darker. Here some of the very much brighter returns which is due to the main met targets. And here you can see there some vegetations are there, so this vegetation have the medium backscatter or moderate backscatter, okay, and it has some ground also. You can see this ground, it is also having a darker return, okay. So basically based on the parameter, target parameter, we can just see the 3-4 parameter, like what is how is the roughness and how is the dielectric constant and what is the terrain, it is the hilly terrain or that one. So we can interpret the SAR image accordingly. Now we will go to the first is the we have seen all the target parameters, roughness, dielectric constant and terrain slope. Secondly, we have to go for in the sensor parameters also. So not only the target parameters affect the SAR backscatter, and there is also the sensor parameters which affect the radar or SAR backscatter. So first is the wavelength. So backscattering is directly related to the wavelength of the microwave pulse as a function of the terrain objects. Radar wavelength should be matched to the size of the surface features that we wish to discriminate. Object appears bright if it is matched the size of the object matches with the wavelength, okay. So if it is matches with the wavelength, means if we are having the small object determination, so we have to choose the smaller wavelength, and smaller means X band is the smaller wavelength, then C and then L. So if we have to go for the small feature discrimination, so we have to use the X band. If we have to go for the large feature geological mapping, so we can use the L band. And also this basically one important property of the wavelength is the penetration capability. So, and the larger the wavelength, and the more penetration will happen. So you can see this is the X band. So if you go for the foliage penetration, so X band, the SAR waves will go from the top of the canopy, so it will not penetrate towards the vegetation, but C band it can penetrate up to some level, but in the L band you can say it can penetrate up to the surface level. So it depends on your application, means what is your application, means if you want to go for the penetration capabilities, then you have to go for the L band. If you have to go for the small target discrimination, you have to go to the X band. And in between X and L there is a C band, which is the compromise between the X and N band, okay. So we have the feature discrimination also and some penetration capabilities. So mostly for the civilian application we will use the mostly the C band for our different studies, and our reset 1A or EOS satellite is also a C band satellite. So how this wavelength is actually depend on the penetration. So it depends on like this one, and the penetration is actually lambda by pi tan theta, okay. So lambda is the wavelength, and if the wavelength is higher, then we have the higher penetration. Okay, so we can have this penetration depth. Okay, so from the L band we can have up to 30 centimeter in the penetration, S around 15 centimeter, C 7.5 centimeter. So it depends on the wavelength and what we are using for our application purpose. So we have the SAR image at different wavelength, you can see. So this C band and L band, so you can see the C band, the SAR image is looking like this, and L band it is looking slightly smoother because it can penetrate. Okay, so when it is able to penetrate, so it will give us somewhat smooth image as compared to the C band, because C band every small feature interacting with the, so it will appear as a roughness is increasing, and here actually it is penetrating the earth surface, so it is actually appearing as a very much smooth surface in the L band. So we have different frequency band. X band we have, C band, S band, L and P band. We have different satellites. Like X band we have the TerraSAR, C band we have the Reset 1 and recently launched EOS 4 Reset 1A, which is a follow-on Reset 1, RadarSat and Sentinel. S band we have the NovaSAR, L band we have the Pulsar 1 and 2 and CSAT, and P band is a airborne NASA JPL ASR, which is the P band. Next is the look angle. So look angle is also a very much important parameter, which is the angle between the slant range and nadir. So as the look angle increases, backscatter decreases. Okay, so backscatter decreases as a function of the look angle. So a large look angle interact more with the vertical features. Smaller angles have more interaction with the horizontal features. So if you have the analysis of the vertical features, so we can use the larger look angles, because larger look angles have the more interaction with the vertical features. So we can use the large look angles for the vertical features, and if we have the horizontal feature study, then we can use the smaller angles. Okay, so like if you can have the different soil moisture study, you can use the smaller angles also. But if you have to like a crop discrimination if you want to do, so that large look angles we can use for the study of the sugarcane and this type of thing, which is the vertical structures. So that is the depends on your application. If and you want to study any vertical features, then you can use the large look angles, and if you want to study the horizontal features, you can you can use the smaller look angles. Last parameter is the polarization. So this is just a glimpse of the polarization. We have the separate lecture on the polarimetry also. So what is the polarization? Polarization refers to the orientation of electric field vector of an electromagnetic wave. So you can see the electromagnetic radiation actually have the two components. One is the electric field and one is the magnetic field. So how this electric field vector is oriented? Okay, so that orientation of the electric field vector is actually the polarization. Okay, so we can have the horizontal or vertical polarization. Means horizontal, this electric vector will have the in the 0 degree. Okay, and in the vertical it has the 90 degree orientation. Okay, so in this horizontal polarization, it will interact with the horizontal features more, and this vertical polarization interacts with the vertical terrain structures. So if you want to have the study of the vertical objects, standing objects, okay, so you have to use the VV polarization. VV means we can send the V and we can receive the V polarization. So we can use the VV polarization there for study of the vertical feature, because vertical means it will enhance the backscatter in the vertical direction, and the horizontal polarization will enhance the polarization for the horizontal feature. So when the radar wave interacts with the surface and is scattered from it, the polarization can be modified depending upon the properties of the surface. This modification affects the way the scene appears in the polarimetric radar imaging, and the type of surface can be often deduced from the image. So as we are sending some signal with some polarization, and when it interacts with the Earth's surface, so it will modify the polarization. It can enhance or it can reduce the backscatter energy. So that change in this polarization, we can just interpret the what type of target feature is there. So this polarization will help in studying the orientation of the geometrical structure of any target, and it is a vertical or it is a horizontal features. Okay, so this polarization is also affect the backscatter energy of a SAR system. So we have the separate polarization lecture also, so we will study in detail of the in that lecture the polarization concept. Next is the speckle. So what is the speckle? Okay, so you know, in SAR image we are in we have some of the very much granular noise there in the image. So speckle is actually because the SAR system is an active sensor and we are transmitting some electromagnetic radiation, and these all radiations are coherent in nature. Okay, so whenever there is a coherent electromagnetic radiation we are transmitting, so there will be some interference. Okay, so there will be a constructive and destructive interference. So that constructive interference is the where the magnitude is very much higher, so that backscatter energy will become very much bright spot. And destructive interference where they are out of phase. Okay, so constructive means they are in phase and destructive they are out of phase. So speckle is inherent in the imaging on the distributed scatter because SAR is a coherent imaging sensor. So as in our ultrasound imaging we are seeing, we have very much speckle in the, because there also the ultrasound waves are there that is coherent in nature. So they are having the speckle effect. So every coherent device will have the speckle due to the constructive and destructive interference of the coherent radiations. So where they are in the phase, they will produce the bright pixel and there will be the dark pixel. And it is in multiplicative in nature because it is a function of signal itself. So here we can see we have the coherent. So when they are in the phase we have the constructive interference, and when they are out of phase there will be a destructive interference. So here for the constructive interference we are having the brighter spots, and for the destructive interference we have the darker spots. So in this image you can perceive some of the bright and black spots, random pixels all over in the image. So that random noise of black and white pixels is called the speckle in the SAR image, and it is a most limitation of the SAR images because it is very much speckle is there. Actually it is not just like an optical image, a very much good looking optical images. It has the very much noisy data which is appearing as a black and white pixels in the form of the speckle. So we have different SAR sensors. So these different SAR sensors like from L band to the C band. So we have the C set which is L band, IIRS, C band, and most in the Indian sensors we are talking about, we have the reset one which is a C band. It is not operational now, but we have the follow on of reset 1A, reset 1 which is called the reset 1A or EOS 4. EOS means Earth Observation Satellite, and it is also a C band. We have the S band also which is called the NOAA SAR, and the L band satellite like LOS 2 which is the L band. And in future, in the next year, we are launching a dual frequency SAR which is the first of the SAR which is have the both the two frequencies like L and S in the single SAR. So there is no space-bound SAR which has the dual frequency, and it is the Indian it is actually joint mission of ISRO and NASA, that is called the NASA ISRO SAR, which is called NISAR, and it has a both the frequency, and it is the expected launch is on next year 2024. So we have launched the last year the satellite which is called the Earth Observation Satellite EOS 4, which is called the Reset 1A satellite. EOS 4 was launched on the 14th February 2022 by PSLV, and it is carrying the C band. Okay, C band synthetic aperture radar, and it is a follow-on mission to the Reset 1 launched in the 2012, and it has the sun synchronous polar orbit and an altitude of 524.87 kilometer. Okay, around 524 kilometer altitude it has been launched. So this is the typical geometry of the EOS. So you have the EOS satellite which is have the it is 524.87 kilometer, and then Nadir. So this is called the first point, that is called the near, that is the actually the swath from here to here, from near range to the far range. And this is called the, how much is the near range, it is around 107 kilometer away from the Nadir. And here the full far range is around 659 kilometer. So it has the capability of looking from 107 kilometer to 559 kilometer in particular direction. So it can either look in the right and or left direction. So this is a right look, and here it is the left look. So based on the configuration, we can choose the satellite either in the left look geometry or the right look geometry. So this is the right look geometry. So it can either see 659 kilometer in the right look direction or in the left look direction. Okay, so it has the different look angles from the 12 degree to the 49 from 12 degree to the 49 degree. Okay, so you can see, and this is the actually EOS4 provides the ability to configure the imaging to any look angle with the step of 0.1 degree. So at a particular look angle from 11.5, then 11.6, and up to the around 49.6 degrees, which it can image, and it can operate in both right and left look direction. So what are the different parameters? So it has the altitude of 524.87, and it is a sun synchronous orbit. Frequency is of C band, it is 5.4 gigahertz. Antenna is around 6 meter in the azimuth and 2 meter in. So as I told you, the azimuth resolution we are getting for the strip mode, it is around 3 meter because it is L by 2. So L by means length by 2. So length of the is the 6 meter, and it has the polarization of different like it can have the single polarization also, dual, full polarimetry also, and the hybrid circular polarimetry. And next is the roll bias, means in the left and right direction it can have a plus minus 36 degree roll bias, means we have this here to here, we can just give the roll angle of plus minus 36 degree. So range coverage from 107 kilometer to 659 kilometer. Look angle is we can vary from 11.5 to 49.6 point, and incident angle it is around 12.4 to 55.5. So these are the actually the incidence angle and the look angle capabilities of the EOS4 or Reset 1A satellite. So what are the different modes in the Reset 1A, which we have the basically the CRS, MRS, FRS1 and FRS2 and HRS mode. So first is the CRS. What is the CRS? It is called the coarse resolution scan SAR mode. Okay, so as I told you, the classical imaging modes are three modes, like strip map, and there will be a spotlight mode, and there will be a scan SAR mode. So for the EOS4, the scan SAR mode is two modes, like CRS, which is coarse resolution scan SAR, and MRS, medium resolution scan SAR. So in the coarse resolution we have the 50 meter resolution, and the swath is around 223 kilometer. Okay, so as I told you, the scan SAR we have very much large range swath, so 223 kilometer we are getting in the swath direction, and we have the 50 meter resolution, and we have the capability of the single, dual, circular and full polarimetry in the CRS, MRS, FRS1 and FRS2. So all the modes we have this one. Medium resolution scan SAR mode, we have the 33 meter resolution and 160 kilometer swath is there. So it is the 50 meter to 33 meter in the CRS, and in the MRS we are having the 33 meter. Next is the two strip map mode. One is the strip map mode 1, strip map mode 2. So that is the fine resolution. So we are because the antenna is of 6 meters, so we are getting L by 2 3 meter resolution in the strip map mode. Okay, and 25 kilometers. So you can see the swath is limited. Okay, so we have the limited swath in the FRS1 and FRS2. So FRS1 will we have the 25 kilometer swath, and here we have the 20 kilometer swath. The next, if we are having the better than 3 meter resolution, we have the 1 meter resolution also, which is called the high resolution spotlight mode, which is called the HRS mode. Okay, so that is the spotlight mode. So full polarimetry is not available in spotlight mode. Other modes we will have the full polarimetry. Okay, so these are some of the basic parameters of different mode: FRS1, FRS2, MRS, and CRS. So MRS is the medium resolution scan SAR mode. So here we are using the 6 beams of the SAR, because I told you the range swath, actually we have different beams in the range direction. So we are using 6 beams in the MRS and 8 beams in the CRS. Okay, so we have different swath, 25 kilometer in the FRS1 and FRS2. But if we are having the this one around full polarimetry, we can have the 20 kilometer swath, and the MRS we are having the 160 and 223 kilometer swath. Resolution we are having around 3 meter in the by 2 meter. This is the azimuth resolution into the slant range resolution. So as I told you, the resolution, we have 2 resolution in the SAR. One is the azimuth, and so azimuth resolution in FRS we are getting 3 meter and 2 meter, and FRS2 we are getting the 3 meter and 4 meter. So range resolution is slightly coarser in the FRS2. Okay, and similarly we have the MRS mode. So in the MRS we are having the coarser resolution in the azimuth direction. So we have the 33 meter and 50 meter, but we are having the very much larger swath as compared to FRS and FRS2. Here in the HRS mode we are having very much limited swath of 10 kilometer, but we have the azimuth resolution of 1 meter and slant range resolution of 2 meter. So we have different PRF ranges also. So PRF means how much frequently we are sending the pulses at a particular time. So pulse repeating frequency is around 2800 Hz to 3200 Hz. In different modes it is differently. So in the HRS mode we have the higher PRF, and similarly we have different bandwidth, 75 megahertz in the FRS1. Here as the bandwidth is decreased, so you can see it is range resolution is decreased. Okay, so C by 2B is the range resolution. So as the bandwidth will decrease, it will affect the range resolution. So here you can see the range resolution is decreased, and the polarization capability, except for the HRS, we have the single, dual, circular, full polarimetry for different modes. So now we can see some of the images. So you can see this is the FRS1 mode of the Dehradun area. So this is the Forest Research Institute, FRI. Dehradun. So you can see here, this is the buildings here. This is the normal building. So here in this image you can see this is all brighter returns. It is a full image. Okay, full view. So it is coarser in, and it is at actual resolution, 3 meter resolution. Okay, this area actually it is in the actual resolution it is presented. So there is the vegetation and some smooth ground here in the FRI, and this is the building, FRI building. So you can see this is appearing as a very much brighter return as compared to the vegetation and ground. Due to the man-made structures it is coming, and it is having the all this structure. It is now you can compare with this with the optical image. So this is the actual the building is there. So it is appearing as a brighter return. So all these buildings on man-made target is appearing as a brighter returns, and this is the field, open surface, open area. So it is appear as a specular reflection and darker in tone. Okay, so this is the FRI in Dehradun. So this is the Ahmedabad scene. So you can see this is the full scene. So brighter areas actually is appearing as a urban thing, a river, and this is lake is there. So this is the actually the actual resolution in this image. So this is the bridge. You can see this river, and this is the bridge in the river. So this is appearing very much brighter here. Okay, in the SAR image, and this is same optical image. This bridge, how it is appearing, and this you can see the urban settlements in the SAR image, and this is in the optical image. And this is the Here's full scene of the Ahmedabad area only. So this is the airport strip is there. You can see this is the area. This here in this image there is the airport area. So the airstrip it is appearing very much darker in this one, and this all things are appearing brighter in returns in the ES4 image. And this is the Mumbai area. So this is the, you can see in this Mumbai, and the date of pass you can see different. It is a recently acquired data only. So the date of pass is around, it is the 22 January 2023, and it is of 6 April 2022. And this is the Ahmedabad, and this is the Mumbai area of 12 November 2022. And you can see here this is the ships in the 3-meter resolution okay, ES4 data of Mumbai area. And this is the actually new bridge it is making from the port area to the Mumbai area. So it is appearing as a very much bright in return. It is in under construction also. This is the Kolkata region. So you can see this is the bridge in the Kolkata, and you can see some small boats and ships in the Hooghly River in the Kolkata. So these all are of FRS1 mode, which is the strip map mode of 3-meter resolution. And this is actually, you can see the bridge in the ES4 image, and this is in the optical image, same bridge. And you can see the brighter returns in the image due to the artificial objects, and water body appears as black. So these are some some images of the US SAR imagery. So today I have told you about the basic of SAR remote sensing concepts, and the basics of image interpretation of the SAR image, and some glimpses of the EOS4 satellite, and some briefing of some modes and parameters and images. So in the upcoming lectures we will have this reset 1A satellite and EOS4 slides in our normal lectures, like data processing 1, data processing 2. We will have the normal SAR lectures, as well as how we will see with respect to the EOS4 sensor. Okay, so for the data processing in point of view, how the data products of the EOS4s are there, raw data products are there, and there is the level 1, level 2. So we will see one by one in each lectures the EOS4 modes, products and applications, and the SAR processings and their applications. Okay, so for today's lecture it's complete from my side. You can post some of the queries. I will try to answer it.